Hi, in this video I'm going to go through the stereo visual slam for UAV navigation and 3D simulation example from MATLAB Computer Vision toolbox. In this example we're going to do the slam algorithm for a drone that is navigating through a city in a simulation environment provided by the Unreal Engine software, which is used for video games and also for simulations, like in this case using a computer simulation for providing a synthetic environment is a very common strategy in robotics, autonomous driving, because we can get cheap data for training and testing. So in this case we're gonna get this three-dimensional environment of a city and also the trajectory of the drone. The drone trajectory and orientation is provided by the simulation as a data set, and we are only gonna get focused on the SLAM algorithm, which determines the orientation and position of the drone, and also the 3D point cloud that is formed by the images of this simulation environment. So the outcome is gonna look like this. We have the point cloud for the walls of the buildings and also the trajectory, and we're gonna use a database with the backup features for the orb features that we are using for each frame to detect if you happen to be in the same place that you already visited. And for example, in here in this trajectory you always visit new places, but once you get here the set of features matches the one in the database, so a loop was detected, and that's the end of the simulation. So this is the Simulink model that's going to be used. I'm going to talk in detail about it in a moment. So the article for this example is in the references of this video in the description section. So you hit open live script and that'll take you to here. So whoops, to here actually. And the example looks very deceptively simple. Just load the data, set the camera information, open the model, and just run the simulation, and that's it. But really the helper functions that are used within the model add up to more than 1,000 lines of code. Okay, so let's run it. First load the data, and as mentioned before, the data is basically the orientation and position. So you see close to 2,000 points for the orientation and the position. So that's the trajectory of the drone that should come up from the Unreal Engine, and we're gonna use that in the Simulink model, and also the focal length, principal length point. This is for the camera. That should be associated with the simulation as well. So this is the name of the model, and we're just gonna open the model with this, and the model is gonna load. Okay, so it's over here. Okay, so the model, I always like hitting Control D, updating the model to see the types of the model. So I put signal dimensions just to see the dimensions of the signals. Okay, so what we have in here, we have this block, which is a 3D configuration. This is the environment, simulation 3D scene configuration, and US city block, that's the name of the scene. And one important block is the Simulink 3D UAV vehicle. So this is a UAV vehicle that we're going to use, a quad rotor, and we put the name. This name is important because that's the same name that we put in the configuration for the scene view. So the view, the point of the first point of view of the simulation is going to be based on this vehicle. So we control where this vehicle is going to be, the translation and rotation, and we do that by providing this vector of 2,000 points and 2,000 rotations. That's the same one that we just loaded in here from the simulation environment. So we don't care about, really in this example, about controlling this. That's a separate topic that belongs to controls, reinforcement learning, or other thing. We're focusing on perception in here and the SLAM algorithm, which is in this block. So we compute the trajectory of the drone. That's the orientation and the location, although we don't provide orientation in here, but we do compute it, and the 3D points of the surrounding environment. You can see here 30,000 points. This is three-dimensional points belonging to the point cloud that should be what we get in here, this point cloud, and this trajectory here belongs to this, and this is a function, a MATLAB function block that is going to visualize and create this three-dimensional plot that we see here. This happens in here, and basically this is some parameters for the limits, and if we see the actual MATLAB function is basically invoking this helper function to visualize. We're gonna see that in a moment. Okay, so for the camera, this is important as well. That we have a couple of cameras because we use stereo camera. Stereo vision is very effective for the SLAM algorithm because for each snapshot, for each frame, you can triangulate using a disparity map between the distance between the points of the two views. We can triangulate them and get the three-dimensional points for each frame. So it's way more precise than monocular vision. So okay, so in here we see that the parent is Simulink vehicle and the position is 0 baseline divided by 0. So if in the case of monocular vision, this will be 0 0 0, but in the Y we have an offset for the left side of the camera, which is baseline divided by 2, and the right side which is negative baseline divided by 2. So we have the two cameras separated in the y-axis, but both of them are on top of the Simulink vehicle, which is the drone. So these cameras are on top of the drone, and the drone is moved by the coordinates. So in the simulation environment, it's going to provide us the left and right stereo images of the drone as they navigate through the simulation, and those images are going to be fed into the SLAM block, which this is the core, the heart of the algorithm that we're working on. And as we go, we are going to plot this three-dimensional plot, but also we're going to display side by side. You can see the vertical concatenation of the images, the stereo image, and we're going to have a video viewer to see those images. And yeah, as mentioned before, the output is the trajectory of the drone, which is the red line, and also the point cloud, but also an indicator if we have seen an image that already was saw before. So all of the trajectory we see new images, except when we get here that we get into a point that we already seen, and at that point this flag is going to be true and it's going to stop the simulation. So let's get into the heart of this SLAM algorithm, which is this MATLAB system function. This is a MATLAB system function, so it's going to point to an M file, an M script, but it's not like this one. This one is a regular raw MATLAB file, MATLAB function, but this one is different. This one is a MATLAB system function. So this is the MATLAB system function. So it's a class that inherits from MATLAB system, and this has to implement some functions, some methods, some virtual methods that provide information for better integration into a Simulink environment. So for example, it provides the input and outputs, and we can see in here that puts the names of the outputs. This is a method that Simulink knows that it can use from the MATLAB system object to get the names. You can see trajectory, map points, and is loop close, those names. Also for the names of the inputs, I left, I right, but also if they have fixed size, if they are complex, what are the base types of them. This is single boolean. The dimensions, 1000 by 3 is determining here the size. The last one is scalar, and this is 30,000 by 3. So yeah, all of that, and also it has the entry points as well for this. As long as the simulation goes and it keeps feeding images, the entry points of these MATLAB system functions are going to be called. And one of the most important one is this one, step impulse. So I'm place a breakpoint in there, and place breakpoint in other important places as well in here, like this. So I'm gonna keep running this, and I already loaded the model. So next it checks if it is PC. This sadly doesn't run outside Windows. So with this command, we run the simulation. We can also use this run command over here, which is the same, but let's just run it through here. And now we're gonna hit we should hit one of the breakpoints. Yeah, so it's loading the view. We don't have views yet, so this is empty. Okay, so we hit the first breakpoint, which is a step in the MATLAB system block. So we are in here to compute the trajectory and the maps point. So first we need to initialize the system. We did not show the invocation of this one, but this gets invoked before, and it's basically getting the parameters from the parameters of the camera are provided in here, and those camera parameters are picked up to create the camera intrinsics, and those are placed in the object, which is this object, the object of this MATLAB system block. So all these camera parameters, stereo parameters, and the image database, this is important because this is the one with the bag of features that are picked up from a file. I think we might have it somewhere around here. But anyway, this bag of features basically is the one that is used to compare the orb features that we are going to compute for each frame to see if we have landed in the same place. This is what the database that is determined to see if we arrive to the same place. It's not really that important to the SLAM algorithm, it's just part of the example. Okay, so we haven't initialized, so let's initialize in the first. It doesn't initialize, so because we don't have all the data, so now it does because we have left and right. Okay, we have a left and right image, and we're gonna rectify them. And for regular for synthetic simulation like this one, this should not be important, but for real cameras, this is important because cameras have distortion, and this helps to rectify them. So first, we are gonna compute the features for the left and right camera, and this basically consists of detecting the orb features from the image, and these are points, the two-dimensional location of those points. And we're gonna select the 1000 with a uniform distribution, 1000 points out of those orb features, and then extract the features for those points. We pass the image and the points, and we get the features, which for the 1000 we get 32, a vector of 32 values, vector values, and these vector values are the ones that are used to match points between two different images. Okay. I'm not gonna go much in detail in this. Please see the references in this video, because I have other videos in which I go more detail about this matching of features and the triangulation and all those things. But in here I had to go very fast because these are more than 1000 lines of code, and I'm not gonna finish if I give too much detail. Okay, so in the initial pose is basically the identity matrix and the 000, because we were in the origin at the beginning. So we pass the left image, right image, and the features in the left image and features in the right image. And with that is enough to reconstruct the three-dimensional points. But this is an internal function, so let's see the details of it. Okay, so first it's gonna find the features from the previous frame. Okay, so how we do that? Let's take a look. First, it's gonna match the points, the features. This is from the left and right. My bad. It's matching the stereo points. So yeah, we're matching them, filtering them. Once we get the match between the points in these are the features in the left and right. We do some filtering according to a epipolar line. And then we get the match indexes, and once we get the match indexes, we take the one that matters, but we're not done yet. We want the three-dimensional points, and for that we get both the left image and the right image and turn them to gray, and use this computer vision toolbox function, a disparitySGM. And this one is going to give us a disparity map, and this one is used to get the three-dimensional points from the two stereo images. Let's take a look at how this looks. If we look at it like this, then it's gonna be plain black and white because the values of the distances are too low. so that doesn't show the whole truth. But if we take the maximum, we see that it's 20. The maximum value is 20 and the minimum should be 0. So let's multiply by 255 divided by 20. So we are scaling it to the uint 8, which is visible in here, and we're going to convert it to uint 8 so that it can be visible. And now we have a better image for the disparity map. And there's another video that I added in the reference to compute the distance of the centroid of a person that is walking in a room. And in that one I explained this pair of functions better. So the thing is that this is going to give you the distance between the points in the two stereo images. And as the farther you are, the smaller the distance is. So it's like if you're moving an object very close to you for 1 feet, that's going to look like a huge difference. But if you take that object very far away from you and move it also 1 feet, the change is going to be smaller. So the same principle applies in here. The difference between the corresponding points in the two stereo images is going to be smaller as you go far away. So you can see black, this means that is background, and the white, the more that is closer to white is the ones closer to you. So this is going to give you a sense of the depth, and that is precisely what this reconstructScene is using, the disparity map plus the camera information. And basically that is going to give you 3D points associated for each pixel. Notice that the images are 721 by 12 1281, and that's the same size that we get in here, but with by 3, because we have the XYZ for each of the points. And yeah, so we're gonna take advantage of those points. This is also a computer vision toolbox function, and with those 3D points in here we're gonna do some processing of the points, maybe some filtering. You're gonna see a lot of filtering in here. At the end we get the pairs that matter, and we have to project those points to according to the camera of the current pose. In this case we have the initial pose, so it's gonna be an identity matrix in here, and also 0, 0, so the points are not really changed, but in the next views they're gonna be adjusted to the camera pose. Okay, so that's about it for this point. So we're still in the main loop, initializing the system, but this is common logic with the main loop. We're gonna see later. Okay, so we have the initial set of three-dimensional points, and these two objects are very important. In most or all examples of SLAM that you see in MATLAB, you're gonna see the imageviewset. This is gonna carry the position and orientation of the camera along with the points of interest of each view. The points of interest are the OR points, fast, brisk, all those points, and also the connection between two frames and the association between points of interest between different views. So that it gives you opportunity to make traces object, and there's a method in this object to give you the traces. And this one is like a database of three-dimensional points, and both of these objects are going to be modified as the drone goes through the city. It's going to keep adding three-dimensional points, improving the three-dimensional points, improving the poses. This also gives you the poses of the camera. So the poses, the three-dimensional points keeps getting calibrated, because as long as you go through the simulation, it gets a little bit off from the reality, and it needs to be adjusted as you go. And then there's a function from MATLAB, bundle adjustment. This is called everywhere. So that's part of what makes the example a little more complicated. This constant adjustment, a recalibration, and an update. Okay, so this is another thing that adds complexity to the example. It's the view and direction depth. See, this is basically an object that is, for this example in particular, that for each point in the image, for each point in the images, you have like a minimum maximum depth, and basically some additional information about the point that it can help you to know if you're doing things right. You have to also update this object constantly. I'm not gonna go in detail on it. Okay, so we are gonna add the first view, which is number 1, as you can see in here. This is view number 1, and you have the initial pose, which is the identity matrix and 0, 0, 0, and the points of it, which we just take the points in the left camera, the orb points, and the features, the orb features. And then we add the three-dimensional world points into the worldpointset. This is the worldpointset in here. You can see it in here. Oh, it doesn't have a preview. Then we have to do this. Okay. Yeah, it's a worldpointset, and you have the 3D points. You just put it there. And notice that that returns also some indexes for those three-dimensional points. So you have we added like 198 points, so you're gonna have the corresponding 198 indexes for them. Okay, so we have to add correspondences. This is important because for each frame we get the features from the last frame, and not only get the feature from the last frame, but also we get the three-dimensional points corresponding to them. And we do that because in the world point set we have an association between the two-dimensional points and the 3D points, and that happens in here. Notice here that we have the three-dimensional point indexes, and then we have the match pairs, which is the indexes of the previous frame of the left images, the two-dimensional points of the orb features. So we connect those points with the three-dimensional points in the current frame, which is number 1 in the world point set. So that we're gonna use later. Okay, so now the current frame index is number 2 because we're moving on to the second view. And add feature images. This is the database to detect that the loop has been completed. With this, the one that has the bag of features. Okay, so we just added there. Okay. Okay, so we finish initialization, and then the current frame becomes the last one, and the current frame index becomes the last one, and we indicate if the loop was detected. And let's continue. And now we're finally going to the main loop. This is the most important part of the SLAM algorithm here. So we again rectify the images. We detect the features, the orb features, the same way in the left and right. Then we again go to the track last keyframe. We take, as mentioned before, we take the last keyframe is number 1, so we take the indexes of the orb points and the corresponding three-dimensional points. So we get the points and the features, which are the vectors of 32 values that we are going to use to match in here. So we match them against the current features, the orb features of the left image. So with that match, we get the pairs that match. And for example, previously we have 198, and now we have 1000 points. But how many match between the previous frame and this one? Only 104. So it's much more or less points that match. So those are the ones that we care. So we filter them out. And once we have the match, we estimate the world camera pose. So we get the corresponding three-dimensional points for the ones that match between the current frame and the previous frame. So we already have the three-dimensional information, and we get it. And that's why we have the world view, a world point set that can give us the association between the previous frame, two-dimensional points, and the three-dimensional points. And now we have these three-dimensional points, or the match points. We give the camera intrinsics, and we give also the match image points. We give the two-dimensional points, the corresponding three-dimensional points to them, and the intrinsics. And that information is all we need to use this computer vision toolbox method, estimate world camera pose, to determine the orientation and the location of the camera in the current frame. Okay, that's one of the big steps. Okay, so we already have that, but notice that we're working with a stereo camera for each, and so we have stereo images for each view, so we can determine additional three-dimensional points. So the work is not done yet. So we get the pose, and again we use bundle adjustment to recalibrate the pose, get the three-dimensional points, get the camera intrinsic. So this is the beginning of craziness in here, because there's a lot of filtering. We use if it is within the radius, we determine if it is within the radius to filter out things that should not be there, and then we use additional filtering. And then notice how we call bundle adjustment twice. We can bundle adjustment a bunch of times to adjust the poses. But the important thing of this is that we got the pose. We got the pose based on the three-dimensional information from the last frame and the matching of the OR points with the current frame. Okay, so we keep going forward. Is this a keyframe? Yes, it is. There's some logic in here to determine if this is a keyframe or not. I guess to make the computations faster, perhaps. Okay, now we're gonna use this method, internal method, to determine the three-dimensional points in the current frame. We can add more points, more information to our world in here. So we pass the left and right image with the current features in the left, current features in the right, current points in the left, current points in the right, and the current pose that we just got using this function above. So we're gonna get these three-dimensional points and the match pairs. Okay, let's go inside here. Again, we get the same disparity map that we saw before. This is the distance between the points in the two bidimensional stereo images. And from the disparity map, we use the reconstructScene and the camera parameters, and we get the three-dimensional points for the current frame. And that's all we need. We get some processing. And now notice that, as mentioned before, previously we had the three-dimensional points in the initial frame, which was an iMatrix, identity matrix. Not anymore. We have some pose in here, so the three-dimensional points are gonna change. The 177 points, new points. So they're gonna be adjusted to the camera pose. Okay, so now we do some additional filtering because there's some filtering here, because notice that there are two kinds of three-dimensional points. One of them is the points of the match points with the previous frame. Those already exist in the database, but then there's some new points that we're introducing here, and we're gonna add them separately into a 3-point database. Okay, so let's add the new frame in here. This is one of the important steps in here. So let's go inside. So in here we get the view ID. We're in number second. So we add the view. We have the pose, the rigid 3D object with the rotation and translation of the camera in the current frame. We have the orb features for this frame, and we have the current points. That's all we need to add a view into imageviewset object. Again, this is one of the most important objects that keeps track of the views. Okay, so now we need to add the new points. I mean, what this is basically doing is adding the connection between the previous frame and the new frame. And then the connection between the features in the previous frame and the new frame, which we already had. There's some pre-processing in there, so we add the connection. And also, in addition to add the connection between the frames in the image view set, we also had to add points in the worldpointset. So we add the connection, but notice that those points that match had the connection in the view number 1. They didn't have the connection in view number 2. So now we are adding the connection for view number 2 of these three-dimensional points, but these should be the points that already existed in the database. These are the correspondence for them. And notice we're passing it then here. Then we need to add the new points. We go a little bit down and we add the new points in here. So these are the three-dimensional points that we obtained from the stereo vision in the current frame, and we added to the world view to the 3D point database, which is called worldpointset. And also we need to add the correspondence of those new points. We need to add the correspondence. That will be the corresponding feature index in this frame and the three-dimensional points. And this is the current frame, which is number 2, and this is the database. Okay, so again, this is another method that keeps improving the three-dimensional points, called more bundle adjustments. I'm not going to go in detail into that. And again, there's this object from this example that gives you a depth and minimum, maximum depth, a corresponding more important frame for a particular information. So this is, I'm not going to go in detail into that. and then more bundle adjustment to further refine the poses and the word points, whatever. And this is the place where the loop is created. It's gonna check on the database at some point in here, and check on this method check loop closer should go into the database and check the features, and if they match, then you have the loop detection, and you get this value set to true to finish the simulation. Okay, so let's just hit F5. Again, it's gonna go to the main loop. This is the main loop. We already seen this. We just went through all of this. So let's just run it. Now the simulation is gonna keep running. It should load the visualization, and there's a function here to visualize. We can put a breakpoint here to see what happens. Well, let's just put it when it goes inside. Yeah, so this is gonna create a point cloud player, and in this point cloud player we pass the word point view. This word point set is the one that is passed to display the point cloud in here, and the trajectory which is this is the actually, if you go to the model, this 30,000 by 3 are the 3D points that are placed into the point cloud, and this trajectory, which is the red line, this red line here, where the drone is, and in the drone is this three-dimensional point trajectory of points where the drone is. This is the one that is displayed in here to plot where you are. So it's being accumulated. The 3 points are being accumulated, and also the trajectory is accumulated. And I think it could be much less than this size, much less than 1,000, much less than 30,000. I think this is the maximum number of points in the trajectory and maximum number of points in the cloud. So all of them are plotted like this, and we see them in here as we go. So yeah, I'm just gonna get rid of this. Okay, so yeah, so it's going through a city. I think it already gave a turn. It's gonna give a turn soon. Let's just expand this a little bit. Okay, so soon it's gonna give a turn. Notice how it's accumulated the three-dimensional points, and eventually it is not, of course, you cannot derive all the three-dimensional points of the information, but the robot usually wants to know where to go, figure out a map, and notice that from the points that we're getting, we can easily create worlds, three-dimensional worlds that represent like a maze, like a labyrinth, and with that information is enough for the robot to figure out where to go and how to avoid to create a plan for a trajectory. Now it's giving a turn, and notice that you're gonna see it also in here. Yeah, so it's very far away from the loop. Yeah, you see it's over here. It just gave the turn down here. Okay, so it keeps accumulating points, as you can see in here. Okay, one thing that I hope that in the future the API for SLAM gets improved. You can see how we call this imageviewset, adding points, filtering points, a bundle adjustment everywhere, and doing a lot of pre-processing of the points and doing a lot of filtering, and it can get complicated real quick, and we get more than 1,000 or 2,000 lines of code just by processing all these points over and over again to filter and filter and filter and triangulate, calibrate camera poses over and over again. And I think the SLAM algorithm it might be better if it is like deep learning. In deep learning, you have a basic, very basic API for the most common case, where you can easily create the layers. You can put the layers stack on top of each other and do a very simple network and train it in just maybe less than 20 lines of code or less. And then you have also the API for the custom training, which is more complicated and is more elaborated, and but gives you the flexibility to do whatever you want. I think the SLAM should learn from it. It should have like a big SLAM object that in less than 20 lines of code you can do things like this for the most common case, but also provide the raw API with the bundle adjustment, imageviewset, worldpointset, so that you can do whatever you want, but at the cost of having these thousands lines of code. And yeah, there should be examples for both of them. That should make life easier for integration as well. Okay, so yeah, we are half in the loop. We're collecting more three-dimensional points. I'm gonna pause this until the simulation finishes. The simulation is finished. It's just detected the final loop, and let me make sure that it's done. Yes, it is finished, and we can see here the final point cloud map. And as mentioned before, this of course doesn't have the full information, but it should be enough to create walls in 3D and create a maze-like labyrinth to be able to have a plan for creating the trajectory of the drone. Yeah, and basically the position should be pretty close enough to the one that the actual trajectory, which is determined by the simulation in this case. Okay, so that's it for this example. Thank you very much for watching.